So last time we were working in section 7.2, and today we're going to finish that up. We left off having just talked about scientific notation, which is a really good break spot for us because we're going to move today into rounding. All right, so there's these are what are considered estimation techniques. Some of them are truly rounding and you get exact answers to a certain level of accuracy, but estimation doesn't include just the rounding that you necessarily are familiar with when I say rounding. So I want to talk about a couple of different ways. The first one is the one that you're familiar with. It's rounding to the nearest, and you see there's a blank there because we can fill that blank in with lots of different things. You can fill it in with something that's bigger than a decimal, right, like the tens place. Or you can do it to a decimal location, like say to the hundredths place. So there's lots of things that could fill in that blank. You're going to find the location that you're going to round to, and you're going to use the digit 1 right after it. And if it's a 0 to 4, you round down, which just means everything else becomes 0. If it's 5 to 9, you round up, which means the place value before increases in value by 1. So we'll do some examples, but there's one other method that you may be less familiar with for estimation, and it's called front-end estimation. Front-end estimation works like this. You use the first value or the first couple of values, and you round off. Rounding off is actually the same thing as rounding down. It just means that everything becomes zeros after it, no matter what they were. Even if it was a 9, it doesn't make something else increase. It always makes everything 0 out. Okay, so that's front-end estimation. So we're going to use an example, and this one is one where it asks us to round to a specific location. So we have the number 203 and 651 thousandths that we're given. And part A asks us to round to the nearest hundred. So 100, what number do you see that's in the hundreds place? That's the 2. So this is the number we're going to be rounding. It's going to either stay a 2 or it's going to become a 3. Those are our only options. If it stays a 2, then everything else after it becomes a 0. If it becomes a 3, then everything else after it becomes a 0. So our options are either that this is going to become 200 or 300. And we make that decision based on the next number that comes after the 2. So in this case, it's a 0. So it's in that 0 to 4 that we just talked about. 0 to 4 means it rounds down. So that means everything else after it becomes a 0. So our number becomes 200. Okay? Because we looked at, I'll have to erase this in a minute, so let me actually copy this down here. Right? The next one, I'll just keep writing it so that I can do some highlighting as we go. 203.651. It says hundredths. What number is in the hundredths place? It's a 5. So everything before the 5 will stay exactly like it is. The 5 will either stay a 5 or it will become a 6. Those are the only options. And we make the decision based on what comes after the 5. It's a 1. The 1 is in that 0 to 4. So it means everything after the 5 goes down to 0. So this is 203.65. The next one, 203.651, says the, 51. Says the units place. So what value is in the units place?
3.
The 3. So we use this place value. We call it either units place or the ones place. Either one are used for this value. So this number before the 0 will stay 20. The 3 will either stay a 3 or become a 4, and we make that decision based on the number that comes after it. That's actually a 6 this time. So what is the 6 telling us will happen? It will go up. So my 3 will increase to a 4. And then everything else after it becomes a 0. So this is 204. Okay? Now some of your problems don't tell you what to round to. And that's an example I think that's happening next. Let's check it out. Yeah. So example number 6 asks us to do 2 things. It asks us to use rounding, but it doesn't say to what place. And it asks us to use front-end estimation, and it doesn't say to what place. So when that's the case, we get to pick. So I'll pick a couple of them just so you can see how it would work depending on what you picked. So I'm going to use, just for our first run through this, to the tens place, okay? And we'll do A and B both to the tens place because it doesn't make sense to compare them unless we do them both to the same place value. So you can see how it works out. So when it asks you to use rounding inside of a problem where you've actually got some kind of computation like subtraction, it doesn't make any sense to do the computation and then round. The point of rounding is to make the computation easier. So if I'm working on this from that perspective, this number 89, the tens place in both of these numbers is, of course, the first digit, the 8 or the 3. So my 8, looking at my 9 next, will do what? It'll go up. So the 89 and the change becomes a 90, right? This is a subtraction problem. I'm just going to write it vertically because my screen has a space to do this in a little bit better order. How about the 32? Well, I look at the 2 next. And what does the 2 say? It'll stay the same. The 3 will stay the same and everything else will become 0, so the number becomes a 30. So again, the benefit of rounding really lies in the fact that the computation becomes easier. 90 minus 30 is much easier to do than 89 and 4700ths minus 32 and 1600ths. It's much more challenging, right? Lots more calculation there. Of course, 90 minus 30 is 60. So this would be using A, rounding. B says that we're going to use front-end estimation. So let's actually look at what front-end estimation does. Front-end estimation says, again, look at the 8 and the 3. They're highlighted in blue here. But I don't care what comes next. The 8 stays an 8, so it becomes 80, and the 3 stays a 3, so it becomes 30. Okay? That's what front-end estimation does. It just zeroes things out. Leaves the number the same and zeroes it out. We do the subtraction. 80 minus 30 is 50. So our methods of rounding or estimation here, rounding versus front-end estimation, don't always yield the same answer, and that's okay. So let's do the same thing. I know it asks us to actually calculate it, and we'll do that in just a second, but let's just do the same thing to a different digit. Let's round to the nearest units now. I think that's the one I want to do. Let me check just a second. Oh, I don't have it written down. It's okay. We'll do it to the units. So up here, if I'm doing rounding, I'm going to be looking at the 9 and the 2, right? So with rounding, the 9 means I then look at the 4. So will this stay 89 or will it become 90? It will stay 89 because it's a 4 that comes next. 0 to 4, I leave the numbers the same, zero everything else out. How about the 32? It will stay 32. And I can subtract this one. This one's pretty nice. I have 7, I have 57, right? Okay. So front-end estimation on this one actually looks exactly like rounding. Because front-end estimation says, again, I look at the yellow, or not yellow, the blue pieces that I marked before. And I just keep the number up to the blue part exactly the same and I zero everything else out. So 89 and 4700ths is 89. 32 and 1600ths is 32. And when I subtract, I get the same 57 that the previous method did. For different reasons, mind you, but the same values actually pop up this time. Okay, so they sometimes yield the same thing and they sometimes don't. And this is an example showing both things. Now, when you're approaching a problem like this and it doesn't give you the place to round to, it means you get to pick. So pick something easy, right? Rounding this to the 10th place would be the most useless on this one, wouldn't it? I'm almost doing the whole problem. Okay, it doesn't prove to be very useful. So rounding to the tens or rounding to the units is both reasonable and it actually simplifies the problem. And then it says, it doesn't actually call it part C, but we'll call it part C. It says to actually do the calculation. So to actually do the calculation means that we're actually going to subtract 89 and 4700ths minus 32 and 1600ths. This one's a really nice subtraction. I don't think there's even any regrouping we have to do. 7 minus 6 is 1. 4 minus 3, 2 is 3. Sorry, 4 minus 1 is 3. 9 minus 2 is 7. And 8 minus 3 is 5. 5731. And you can actually see that all the answers, even from all the way down to 50, all the way up to 60, are all in the ballpark of the right answer, right? They are. They're all close. And so that's what's going to happen anytime we do any rounding or estimation, is they're going to be close. Okay, for the last example that we're going to do together, it's going to take us a little bit of work, okay? You need a calculator. In particular, if you have something that is like a TI 83 or 84, that's super friendly. If you don't, it's okay. A scientific calculator will work just fine. So let's take a look at that problem together so you can see what it is that it's asking. So this is a type C question from our book. A student tries to calculate 999 thousandths to the 10,000 on a calculator and finds the answer to be 4.5173346 times 10 to the negative fifth. Okay, scientific notation, it's a very, very small number, right, because the exponent's negative. This is a very small decimal. The student wonders how it is that you could raise a number like 999 thousandths so close to the number 1, right? That's very close to the number 1. Right? If you saw that on the gas tank, which you might have seen, like a year and a half ago, you would look at it and you'd say, I'm paying $1 a gallon, correct? Yeah, you would see it's $1 a gallon. But when you raise it to a power, normally when you raise a number that's the number 1 to a power, you get close to the number 1. So why is it that this number is actually very close to the number 0? So we're going to explore that a little bit, and I'm going to walk you through how to think about that and why that's actually happening. So we're going to consider taking that same 999, but we're just going to square it to start with, okay? So we're not raising it to the power of 10,000, we're just squaring it to see what happens. So any scientific calculator can take this particular problem for you. And if you do that, you'll get 0.998001. Okay, still very close to the number 1, right? It is worth noting, however, that it's smaller than 1. And it's smaller than the 999 we started with, but it's still really close. And what we're going to do is we're going to square it again. So I don't mean that we're going to take it and we're going to take the 0.999 and write it out that way. We're actually going to take this digit, the 998001, and we're going to square it. Okay? So we're going to square the numbers, and we're going to keep doing this squaring process each time. So if your calculator, scientific calculator, you should just be able to hit the square button, and it takes the previous answer and squares it. That's why I'm doing that, is because it moves through the process pretty quickly. But what we're actually doing at this point is 0.999 to the 4th, because I've squared something twice. You square it, you square it again, it's actually to the power of 4. So this is equivalent. I'll write the equivalencies down as we go. And as you do this, you should get 0.996006. I'm going to use 6 decimals as we go. It's sufficient and without cutting things off too much. Okay, so far so good? It got smaller, right? It did, but still not significantly. Agreed? I'm nowhere near 0. I'm still really close to the number 1. And we're going to do it again. This is like dot, dot, dot vertically. Dot, 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 and again, and again, and again. So now we're going to do, actually I probably shouldn't write equals here, but we're going to do the 0.996006 that we just got, and we're going to square that. So if we square the 4, we would be multiplying the exponents. This is actually the same as raising this to the 8th. 4 times 2 is 8. So if I square this again in my calculator, I get 0.992028. Okay, so now we're going to take the 992,028 and we're going to square that. So again, if we're squaring something that's raised to the 8th, I now multiply the 8 times 6, the 2 to get 16. I've got the 16th power that I'm actually doing at this point. And I finally have something that's not 99 cents, right? It's 4119. We're going to do this iteration a few more times. Okay, we're just doing the same thing. We're squaring it again. So 0.984119 squared. So that takes my power of 16 to what power? It's a 32 power when I square it again. And when I do that, this time I get 968,491. Okay, trying to give myself more space. We'll see what happens when it goes to writing again this time. All right, so we're going to take that and we're going to square it again. So I have my 968,491 squared. So what is that new power that I've really raised it to at this point? 64. When I do that, the number is finally changing in a more dramatic way. 0.937975. Okay, the jumps are becoming bigger in this squaring process. You might feel like, well, I just squared it, but really what did you see change? You saw this exponent change significantly from 8 to 16, 16, 32, and 32 now to 64. Those are pretty big jumps, actually. So if we square it again, what power am I actually working with at this point? It was 64 last time. 128 is right, yeah. And lo and behold, I'm no longer in the 90s. 879797. We're going to do a couple more times. We're real close to stopping and making our discussion point. But our 87 finally shows we're out of the 90s. 879797 squared. What power am I looking at this point? You're right, it's 256. And I bypass the 80s altogether, and all of a sudden I land at 774043. Okay, we're going to do it actually exactly 2 more times, and then we'll have a stop spot. So I have that same 774043 squared. What power am I actually doing if I do that? $512 is right. Yep. Every time they're just multiplying that power by 2 is what's happening if you're not catching that, guys. That's 599142. I'm going to shrink this one last time. Okay, and then I'm going to do last time, so 0.599142 squared, which is the same as 0.999 to what power? Yeah, and that's why I'm stopping here, is because I'm basically a tenth of the way there at this point, right? I mean, my number's 10,000, I'm at 1,000. So this actually puts me all the way down at 358,971. So what we've done is what's considered a recursive process. We've done the same step over and over and over again recursively. You might remember that word from number theory. And so we need to answer the question of what's happening. Why is this happening? This isn't, of course, the only way to justify it, but I wanted you to see what's happening because it's sort of a counterintuitive fact that this is happening. I've raised something that's really close to 1 to a power high enough that all of a sudden now I'm at 0. So what's actually really happening? Well, whenever you multiply by a value, let's say by a positive value, so that we can stick with this being positive. Positive value less than 1. Right? So 1/2, 2/3, 0.76. In this case, it was 0.999. Right? Anytime it's less than the number 1, but still positive. Your product, right? The answer to that, your product becomes smaller than your initial value. Here, like in this problem, we are doing this namely multiplying by a value I should say positive value, just to be clear, by a positive value less than 1. $10,000 times. Now, we did the power 2 every time, so it's not like we showed what happened at, squaring, cubing to the 5th, to the 6th, to the 7th, to the 8th, to the 9th. We didn't do it consecutively, right? We made these jumps along the way, which is why we saw these jumps in the values happening over here more quickly. If we did it individually, it would take us too long to recognize that's really what's truly happening here, so that's why we did it that way. But that happens. Every time we multiply by something smaller than 1, still positive, our value will become smaller. And I really sort of make a big emphasis to that because when kids start working with fractions and decimals, this is counterintuitive. And it's counterintuitive because somewhere in elementary school, somebody told them, when you multiply, things get bigger. And they do when you're working with whole numbers, right? 2 times 3, it gets bigger, becomes 6. And so all of a sudden now what, the 3rd grade or the 2nd grade teacher said and said over and over again probably is no longer true. And that's not a good thing. So if you're that 2nd or 3rd grade teacher, please do not tell your students when you multiply things get bigger, because they actually don't always do that, especially not when we get to fractions and decimals. So thought I would mention that here.